Today we're going to take a little closer look at this, what we learned yesterday about valence bond theory. So valence bond theory, if you'll remember, is when these orbitals that we've learned, okay, when they bond, they'll bond either in a sigma bond or a pi bond, like this. What we didn't talk about is that the fact that these bonds, the shapes of these orbitals will actually change. So that's what I want to focus on today. When atoms are bonded with other atoms, these start to hybridize, or like the p orbital can become more like an S becomes more like a p. We're going to look at what that looks like, and we're going to focus mostly on carbon because that's really what this whole unit is about carbon chemistry. How I've kind of explained it, we're just going to go over orbital notation for regular carbon, and then we're going to do carbon with a single bond, carbon with a double bond, and carbon with a triple bond, and see how those orbitals change depending on what types of bond the carbon is undergoing. So first thing I want to do is draw the energy level going up. So energy level is increasing right here. If we look at carbon, we're just going to look at carbon alone. So carbon, if it was not bonded with anything. And one thing I do want to just kind of go over first is what this hybridized orbital means. You can have an sp3 hybridized orbital. And what that means is that you have one s orbital, one p plus another p plus another p. So sp3, that's what that means. sp2. When carbon is sp2 hybridized, that means it has s plus p characteristics of each of these. And I'll show you what that means in a minute. Then we have sp hybridized. Okay, carbon can be sp hybridized, and what that means is that it is 50% s and 50% p. So we're going to just keep this here so that we can reference them later. So we're going to talk about carbon alone, okay, so we have carbon alone, and then we have carbon sp3 hybridized, then we have carbon sp2 hybridized, and then we have carbon sp hybridized. So we're going to look at all of those today. First, I'm going to draw the orbital notation, and then we will draw the orbitals and how the bonds look using the orbitals and not just a ball and stick method. So when I say a ball and stick method, I mean, like, for example, methane. Okay, so methane, ball and stick, I guess, would be carbon in the middle. Methane is CH4. So you have a carbon in the middle, a hydrogen up here, and 3 hydrogens sticking off of it, like that. Okay, so that's methane, it's tetrahedral. So we're going to look at this and then what the orbitals look like and what the orbital notation looks like after they change using these bonds, because everything you've learned has just been carbon alone. So what you've learned is that carbon has 6 electrons, right? If you look on the periodic table, it's atomic number 6. It has 6 protons and 6 electrons if it's neutral. So 6 electrons would mean 1s2, right? And it would have 2 electrons in there. And then we would have another s, but in the second energy level, 2s2, okay? That's 4 electrons. And then remember, it goes up to p, right? So we have p, but then that would 2p, and we have 2 electrons in the p orbital. Some of the, I guess, misconceptions or something you learned wrong is that the p orbital only looks like this, right? So sometimes when I draw something with p orbitals or in the second p shell, don't forget that the p orbitals are actually, there can be up to 3 of them, right? There's px, py, and pz. Okay, so what I'm talking about is this right here. There are 3 p orbitals, which you guys usually are okay with that, but when we actually draw them, it kind of freaks you out a little. So we have 3 p orbitals. So this red one is py, right? That's along the y-axis. You can also have px, right? And that is a p orbital along this axis. You can also have pz, which is If you'll picture this going backwards behind the rest of the atom, and then this one coming forwards, coming out of the paper, that's on the z-axis. So those are each p orbitals. And each p orbital can hold up to 2 electrons. So this one can hold 2 electrons, this one can hold 2 electrons, and this one can hold 2 electrons. So that's how the p orbital can look. This is carbon if it's not bonded with anything. However, that's not normal. Carbon is normally bonded with something. If it's not bonded with something, it's undergoing a reaction to bond with something. It doesn't just sit alone. We're going to ignore this. And if you've been in class, you guys already know why we're ignoring it. So when we draw carbon with the Bohr diagram, Bohr-Rutherford, right? We have 2 electrons in that first, and then we have 4 valence electrons, right? And that second energy level. Now, we're ignoring 1s2, okay? That's the first energy level. We're ignoring this because these have nothing to do with bonding at all. Really keeping track of these will just be annoying and a little confusing and cloud the drawing more than what you're going to see. Anyways, so I am not looking at this, but know that it still exists. It's still there. It doesn't go away. Just know that we're not going to be drawing this when we draw our orbitals overlapping because it just makes a mess. But no, it's still there, and we're manipulating these orbital notations here. But the 1s2 never changes no matter how many bonds carbon gets. So moving on, we're going to look at carbon sp3 hybridized, which is with methane. Then we're going to look at ethene, which is carbon double bonded with another carbon. So basically we're looking at carbon in any way possible that you'll see it in your test. And then we'll look at ethyne, which is like acetylene. Well, not like, it is. That's like the common name, I guess, is what I'm trying to say. With a triple bond. So we're going to look at a single bonded carbon, a double bonded carbon, and a triple bonded carbon. If we want to look at carbon alone, okay, let's just draw carbon just to make sure we have like a base. So carbon has s orbital, right? So s is spherical. We're assuming this is the nucleus. So s is spherical, okay? So it has an s orbital. Then it has 2 p orbitals. So we're going to put this orbital on the x-axis, and we're going to put another one on the y-axis. Honestly, it doesn't matter because, like I say in the class, I mean, these molecules turn and spin, so you could have put it on the z if you really wanted to. It doesn't matter. So this is what carbon would look like, okay, if it wasn't bonded with anything. So let's look at what it looks like bonded with something. When it bonds with something, that causes hybridization. So what that means is these electrons can actually jump from here to here. So what that means is we no longer have a separate s like this and then 3 p orbitals. They all, with this one, we have a sigma bond here, a sigma bond here, a sigma bond here, and a sigma bond here. Sigma bonds cause hybridization. So since there are 4 sigma bonds here, we have 4 orbitals. So they're going to cause 4 identical orbitals. So what that will look like, instead of an s and then 3 p's, we will actually have 1, 2, 3, 4 identical orbitals, and each of them will be sp3 hybridized. What will happen is this electron will move up here, and each orbital will have 1 electron spinning up according to Hund's rule. So this is what the new orbital notation would look like for carbon with a single bond or a sigma bond. These orbitals no longer have an s character and a separate p character. They all have the same character. They all are identical. So they will all look like 25% s and 75% p. So they'll have a little fatter top or bottom, it doesn't matter, they can flip around, whatever. So they're no longer a circle and a dumbbell separate. They are the exact same thing because they are exact same bonds, so they are the exact same shape. So each of these orbitals will have 1 electron in it. So think of these as like little balloons and kind of pinch them together into the nucleus. So what that means is we have this nucleus, right? We have this nucleus, and we're drawing the orbitals now of an sp3 hybridized carbon. So we have the axes, right? So we have y, XZ. So we're going to draw, it doesn't matter which one you draw first, and it doesn't matter if you put this over here or whatever. Eventually, when you draw your molecule, you kind of want to get it a little close just so you can visualize it, but you're not always going to make it look identical, and that's okay. So you have a sigma bond with here, a small and a bigger one. That's one sp3 orbital. And we're looking at only carbon right now, only carbon. Now, there's another sigma bond. There's 4 of them, so we're going to draw 4 of them. Okay, so we have one like this, and then we have one like this, and then we can draw one like that. And so what this is this is carbon's nucleus right here with electron here, 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 and here. Now, we still have the hydrogens to look at. We're going to draw the hydrogens on there so we can visualize what this whole molecule will look like. So hydrogen is an S block, so it's going to have, we're going to draw a hydrogen here. That's the nucleus of hydrogen. And then there will be overlapping here, and this is where the bond is happening. Then we have another hydrogen here. This is hydrogen's nucleus, and then we have a bond right there. Okay? And we're going to do the same thing for all 4 hydrogens. And all 4 bonds happen right here. This is what methane looks like, or CH4 looks like when you add the orbitals. Okay, so this is what when you look at an electron microscope or whatever, when you're looking at the actual molecule, this is what it looks like. A bunch of little clouds or balloon animals, to me it looks like. And that's what the orbital notation of an sp3 hybridized carbon looks like. Moving on, let's look at a carbon with 3 sigma bonds. So remember, we're looking at only one carbon. Eventually we're going to draw the whole molecule because honestly this carbon is connected here, so we need to draw at least this carbon to connect here. Then by drawing this carbon, we really might as well just stick the 2 hydrogens on because it's just circles and we can visualize the whole molecule. But when we are looking at anything in this unit, we are looking at single central atoms, and I will always indicate which atom you're supposed to look at with like an arrow, or I'll tell you the first carbon, which means this one or whatever. So carbon, this one, all right? We see that this is a sigma bond, a sigma bond, a sigma bond, and then we have a pi bond, okay? So this is our first pi bond. So anytime you have a pi bond, you must have a p orbital. That's the cool thing about the ones who speak Greek, is that this literally is p. So in order to make this bond, you have to have a p orbital. We only have these 4 orbitals initially, right? So one orbital, this is still going to jump up here, but one orbital is going to stay as a p orbital. So one orbital will stay as a p orbital, and only 3 will be hybridized now. The 3 will be hybridized will be the s and the 2 p's left. Okay, so one will stay a p, and the 2 p's and the s will hybridize. So then that looks like this, the orbital notation. So we have 3 hybridized orbitals, sp2, and a p. So some kids, Athenitis, asked, why is this p higher? So if you'll look here, these are certain energy levels. That means p has a higher energy level than this s does, right? When we hybridize them, they're actually in the middle. So this one right here, it's like 75% p and 25% s. So it's kind of like right here in energy level. Here, it's going to be closer towards the middle, but not quite the middle in energy level as far as how much energy is held within these bonds. Let's take a look at what this molecule will look like. So again, 1 electron for each orbital. So it still has 1 electron in each, and they're going to look different. So sp2, it'll have a little more s character than it did on here because this was 75% p and 25% s. This will be 33% s and 67% p. So what these orbitals will look like is a little bit fatter, okay, than these. It's having a little bit more s character than even the sp3s. So they're having a little bit more of that circular character on one side, and that one side will be between the 2 bonds. And then this p orbital is just a normal p orbital, the long and skinny one if I draw it correctly. So this is what the orbitals we will be using for that one atom. Now, these are identical carbon atoms, right? They each have 3 areas of bonding. They each have 2 hydrogens sticking off, and they each have that double bond between them. So we're going to draw both of them and see where these things line up. Now, we don't just have these 4, right? We have these 4 on each dot, right? Because there's 2 carbons. So let's do this dot and then we'll do this dot. Each carbon is identical, so we'll just do it twice. So this carbon, let's do the axes. So again, remember, picture this axis kind of coming out towards you. We're going to draw in different colors, okay? So what I want to look at is first we're going to draw the hybridized orbitals. First, one will be here. So that will be a hybridized orbital right there. And it's going to bond over here with that carbon's hybridized orbital, but we'll wait. Then we will have another sp2, and these right here will be bonded to the 2 hydrogens. These are the other 2 sigma bonds, okay? So that will be one here, one here. Okay, so those are the 3 sigma bonds, okay, that came from here. Then we have a pi bond. And by pi bond, I mean a p orbital, sorry. So we have a p orbital. So this is what the orbitals of carbon look like if we just have 1 carbon here. But let's draw the rest of the molecule so we can visualize it a little better. Let's draw the things connected to this carbon. So the things connected to this carbon, the easy ones and obvious ones, will be hydrogens, right? We have 2 hydrogens here. And let's draw them in their little s orbital. So then there's this overlap, valence bond theory. So that's our hydrogens. And then now let's draw this carbon. I'm going to draw with the same color scheme so we can kind of visualize it. So this carbon has the exact same, right? It's the exact same carbon as this. It has a double bond, it has 2 single bonds, just like this one. Double bond, 2 single bonds, same atoms connected to it. So we're going to draw it basically like a mirror. This is like the bond area here. This sigma bond, the head-to-head sp2 hybridized orbitals, this single bond is the sigma bond. It is that first bond because it's head-to-head. Do you remember the day 1 we looked at head-to-head? That's this bond right here, okay? It's not obviously not P to P, but it's what I want you to see is that head-to-head bonding, and that's the sigma bond here. Then we have another sp2, and these are also going to be towards the hydrogens, right? The sigma bond goes for hydrogens. And don't think of them as right on top of each other. Think of this one, maybe if I color it in really dark, like that. This one's going backwards, and this one's coming towards you. Maybe you can think of it like that, but they're kind of flat, and it's like backwards and forwards. So don't think of them as like, why is it right on top of each other? It's actually, they're spread out a good amount. We have a hybridized. So we have our 3, and then we need our pi bond. So this pi bond, the other p orbital, like this. So we've drawn the other 2. Might as well draw our hydrogens overlapping. Now, one thing I want you to notice is if I were to draw this correctly, which I don't think I've ever successfully drawn it correctly, these 2 should be overlapping, but I always never do. I don't know why. But these 2 are overlapping and bonding. So this is that pi bond, if I were to do it correctly. So these 2 are actually bonding. They're overlapping. So what you're looking at here is that pi bond with the p orbitals. And this, even though it looks like 2 bonds, it's only 1. So this is your 1 pi bond, and then this is your 1 sigma bond. So that's what an sp2 hybridized carbon looks like. Now, what if there are only 2 groups that carbon is bonded to? So with a triple bond, sp hybridized. sp hybridized, I didn't actually explain this, sorry, but sp3 hybridized is when carbon is bonded to 4 groups. So there's 1, 2, 3, 4. It could be 4 chlorines like chloroform. It could be 4 hydrogens. It could be 4 carbons, whatever, bonded to 4 groups. This sp2 is when carbon is bonded to 3 groups. So that's 1, 2, 3 groups that this carbon's bonded to. This sp hybridized is when carbon is bonded to 2 groups. So you have 1, 2 groups. Now let's take a look at what this will look like, and that'll be what we finish off with today. So again, we're looking at the bonds real quick. This sigma bond. Then one of these bonds will be sigma. And then we have these 2 bonds, which are each a pi bond. So we have 2 pi bonds and 2 sigma bonds. So what do you have to have a pi bond? If you recall, over here, we had 1 pi bond. We have to have a p orbital. Now we have 2 pi bonds, so 2 of these p orbitals will remain p orbitals. So we have 2 p orbitals. Then we have 2 sigma which are hybridized, right? They are sp hybridized. And again, each of them, since carbon has 4 valence electrons, we fill them in according to Hund's rule. So that's what our orbitals look like. And now it's 50% character S and 50% P character, right? So it's going to be pretty close to a little circle. I know they look very similar, and I'm not going to judge your artwork. That's not really what I'm going to make you do on the test. And then, but I'm trying to like explain it. And P will be more elongated like a dumbbell like we were used to. So now what we're going to do is you need to know that each one of them will have their electron. And we're going to draw this molecule using these orbitals. Again, we have 2 identical carbons. So we have 2 identical carbons, and then each of them will have their axes. So we have our carbons and the axes along their nuclei. So first we're going to draw these 2. We're going to draw this carbon first. Like we did last time. 1 sigma bond goes here. So this is sigma is the hybridized. So we will draw this sigma here, and then we'll draw the other sigma basically on the same plane, because it is linear, so you do really kind of need to make it linear here. So those are the carbon's 2 sigma bonds, all right? Now we have to look at the 2 pi bonds. You might think you have to draw the p's here, but you don't, because remember, pi bonds are side to side connected, okay, with only p orbitals. So what that will look like, p orbital here, okay, p orbital here, and they should be overlapping. I got close this time, but I'm not quite there. And then you have a p orbital here, and remember this part's actually coming out of the page. So I'm sorry, I know I'm taking a long time, but this is coming out of the page. Some of you guys who actually heard this lecture in class know that I'm really bad at actually drawing orbitals. And this is going behind, and I should have drawn these first. All right, so picture this actually behind this red one. So sorry, I'm a horrible artist, I know. But maybe I can do this. I don't know, I know this is a little extra, but there. This will be a little better. There we go. That makes me feel better. I'm sure I have an illness of some sort. All right, so you can actually see that this bond, what I'm really getting at is I want this p orbital to be back behind the page and this one to be in front. So now we're going to do the same thing with this one. This one's going to go back behind the page, and back here, this and this one are going to be bonding together, and then up here, this one and this one will be bonding together in a pi bond, side by side. If you can visualize this, back here, these 2 dark p orbitals are bonding back here and right here. These 2 p orbitals are also bonding together. So what are we looking at? Let's draw our hydrogens. So we have a hydrogen and a hydrogen. So this is the molecule that we're looking at, but where are all of our bonds? So we have a sigma bond here where the 2 reds bond. That's the sigma bond. Then we have the bond between these 2 p orbitals. It's not these 2 p orbitals, it's one of them. One of this one bonded here. That's 1 pi bond. Both of these 2 are 1 pi bond. The second pi bond, so we have the sigma bond and then 1 pi bond. The second pi bond is with these darker ones, the bond right here. That's your second pi bond. This is what carbon actually looks like when it bonds with things, and now you know that the orbital notation isn't black and white like this. It does change depending on what the carbon's bonded with.